Everybody was given a wood block of shape similar to this and asked to measure the length of this side or edge, the length of this edge, the length of this edge, and the length of this edge. In other words, set flat on a tabletop of the positions of the tops of these things. So, typical set of measurements. The vector from this point to this point is what? Well, the x goes from 0 to 4, so the vector would be 4i. From 0 to 0, of course, is 0, so there's no 0y component. And from 17 to 19 is 2 units, so we have 2k. So between these points, a vector from this point to this point would be 4i plus 2k. Similarly, vector from here to here, negative 4i plus 6j minus 6k. A vector from here to here, you can verify negative 4i plus 3k. So we calculate a normal vector, a vector perpendicular to what we think the plane of the top of this object would be. And we just take any two of these vectors and do their cross product, and we get a normal vector. Well, we do the cross product of the first vector with the second vector, and we get this. Okay? So if we accept this, and we haven't totally verified that this is consistent, for example, is this vector parallel to the vector you'd get if you did the cross product of this one with this one, or this one with this one? They should all be parallel, but since we're doing measurements, we know that there are likely to be slight discrepancies. In any case, we ask then if our normal vector that we got here, based on this vector and this vector, is in fact perpendicular to this vector. To determine if it's perpendicular, we take the normal vector, which we calculated here by the cross product, and we do the dot product with this vector, and we find that the dot product is like 120. Okay, well, 120 seems like a pretty big number. That's maybe a pretty big discrepancy. So our conclusion is that the 4 points aren't in the same plane. That 4, 6, 10, the vector, or the point that we used to get this vector, is not in the plane defined by these three vectors. Okay, now is that a big error? Well, if we think about it, the magnitude of this vector here is on the order of between 30 and 40. Okay, and the magnitude of this vector is 5. So the product of the two magnitudes is somewhere in the vicinity of 120. Well, 120, 150, 200. 120 is pretty far off. So this doesn't seem to confirm that this point is in the same plane as these 3 points. Let's make sure I didn't mess something up. Negative 12 times negative 4 is 48. And then the k's, 24 times 3 is 72. Yep, that's what we get. So we determined there's a pretty significant error there. Okay, it's been a while since we did this. So, okay, what's the equation of the plane through the first 3 points? Okay, let's just take the first 3 points as good and don't worry too much about why this point doesn't seem to be consistent, because I probably just made up these numbers. The equation of the plane through the first 3 points will have the property, well, here's your normal vector, which we calculated, and that is the normal vector through these 3 points of a plane. That's the vector normal to the plane defined by these 3 points. Okay? Here's a point, x naught, y naught, z naught, which could be any point on the plane. And of course, it could be any one of these 3 points, because these 3 points are on the plane through these 3 points. X, Y, Z is an arbitrary point in the plane. X, Y, Z will be in the plane if the vector from x naught, y naught, z naught to x, y, z is perpendicular to the normal vector. Well, the vector from x naught, y naught, z naught to x, y, z is just this, x minus x naught times I plus y minus y naught times j plus z minus z naught times k. So our condition is that x, y, z is on the plane if the dot product of this vector with the normal vector is 0. Okay, well, then we picked this point, 4, 0, 19 for the x naught, y naught, z naught, and we plugged it in here, and we get this condition, that this vector here, just obtained by plugging 4 for x naught, 0 for y naught, 19 for z naught, dotted with this normal vector that we calculated is equal to 0. We do the dot product, we get this, and we then collect in our constant terms. Negative 12 times negative 4 is 4, and 24 times negative 19 is 400, and 24 less than 480, 456. Subtract the 48, we get, well, negative 456, and 48 gives us our negative 408. Okay, so this is the equation of the plane. So all three of these points are in the plane. We can check this out. All these points had better be in the plane if we calculated it correctly. We plug 0, 0, 17 in here and see if we get 0. We plug 4, 0, 19, x, y, and z, and we should get 0. We plug 0, 6, and 18 in, and we should get 0 once more. You can do that. And then, as expected from what we saw here, this point would not be in that plane. We can check that out also. If we plug these numbers in, I claim that we get 80 equals 0. And let's just verify. Let's see, 4 times negative 12 is negative 48. 6 times 16 is 96. That gives us plus 48. 240 and 96 is 336. 336 should be 338, or 228 minus 408. Not sure it gives us 8 equals 0. You can check it out. In any case, we don't get 0 equals 0. This point is not in this plane.